And here's a curb cut. Remember the curb cuts we talked about earlier? Here's a curb cut that meets all the checklists for being a curb cut, but there's a problem, isn't there? All right, this is Vince Cerf. He is chief internet evangelist at Google. He helped invent the email protocols. He did this because the proof that it was useful to him was his own experience. His wife is deaf, and electronic messaging was the only way to reliably communicate with his wife during the day. And even he says, accessibility is not pixie dust you can just throw in at the end of the design process. So, the big message that I have for you today is that accessibility is not just a requirement. It is not about a checklist. Accessibility is your design tool. It's where we're going to find the next innovations, the same way we did when we started designing for mobile devices. Because the things that people with disabilities want and the things that fully able people want is basically, this Venn diagram is basically a circle, okay? It's just on us to find out what this little sliver of things is and to find out that everybody actually wants those same things. So, let's not think about disabilities. Let's just think about people. It's spelled accessibility, not disability. Accessible design is about good design for everyone, whether it's a vegetable peeler, whether it's a curb cut, or whether it's the apps on your phone. Thank you.
Okay, we've got time for questions and answers. Who has a question? And over here. Do you want to come up so we can hear you, and then we'll repeat the question, or if you'd like, you can speak into the microphone, being aware that tonight is being live streamed and recorded. Ooh, you okay?
I now feel so like questioning whether my question is any good. What disability or other impediment is often overlooked the most?
That's a good question. I would say in the field where I operate, motor disabilities is probably overlooked the most because everybody begins with a screen reader. But there are a host of assistive devices that people will use. So if you, say, have severe carpal tunnel, you might just use your keyboard to access the web, to navigate the web. If you are severely disabled, you might only be able to activate a switch device, which basically gives you left, right, maybe a button to press. If code is written correctly from the start, though, regardless of input device or what sort of technology they're using, even a very, very basic device that's essentially a joystick with a button can still be used to navigate the web.
Thank you. Next question, over here. You don't have to come up if you don't want to, but this is as far as the microphone goes.
Oh, I want to come up. So, when we are designing for digital accessibility, can you explain what is actually the difference between a link and a button?
Okay. This is my boss, everybody. All right. How many coders do we have in the house? All right. If it goes somewhere on the internet, it is a link. But if it does something, it's a button. So if I click on something and my URA changes, please code that with an A and an href and a valid URL. But if I'm doing something like opening a menu and I click on this button and the menu pops up, please code that as button. Not only will this make sense to screen readers, but you'll write a hell of a lot less code, okay? Because Both of those things, you can use a very simple jQuery listener event on click, and you're done. You get to go home. The vast majority of you did not want to know that. But now you do, forever. It's baked into your brain. You're welcome.
Okay, we have time for a couple more questions. At the back there. Thanks for coming up. I think having the people coming up actually adds some flavor to the event. Yeah.
Yeah. So you mentioned that doing the accessibility gave you interesting insights when you started looking at the outside sides of the bell curve. What is the most memorable insight you've gotten when looking at the differently abled access?
For me, the biggest insights have been in the ability to simplify my code. That is one level of it. Things become much easier to maintain because I'm writing less of it. But the most powerful thing I saw was at a previous job, we did redesign our site to put accessibility first. We did a lot of super basic stuff. And with the same amount of traffic overnight, we saw a 30% gain in lead conversion. Same content, just a more accessible experience. I'm not saying that people with disabilities suddenly flock to our site. I'm saying that we just made a better, faster, stronger experience for all of our users, and they responded to that. So I've seen it, and I continually see it every time at T-Mobile where we design something with accessibility in mind. It just works better, and it's great.
There's a question at the back there. Is there a second one so we can have that person lined up? Second question. Here. Okay. After.
Hi. At T-Mobile, what kind of projects do you work on that actually have shipped that are accessible internally or externally?
Yeah, so the question was, what projects have I worked on at T-Mobile that have shipped yet? I started there in November, and my role is primarily as the accessibility coach to help teams develop new projects. So if you are a T-Mobile customer and you're into T-Mobile Tuesdays, you're going to get a very good experience when you try to redeem your T-Mobile Tuesdays offers. Also, that the T-Mobile Tuesdays app is actually doing real well. And if you're trying to pay your bill, that works a hell of a lot better now too. In terms of like highly visible projects though, I basically spend a lot of time really just coaching and mentoring developers. And if you are a dev, you know that you work on something for a couple of weeks and it takes a month to ship. So we're still getting there. But yeah. T-Mo Tuesdays.
So for context, I spent a few months at my old job basically being the only one who wanted to work on accessibility. And I had to kind of band-aid a code base of spaghetti code that wasn't accessible. So what are your tips for people who do have to band-aid a code base and make it like accessible in a good way, not just in a, checking the boxes way?
Okay, so the question is, if you are left with that Band-Aid sort of solution, or that your Band-Aid sort of situation, how do you do it? The answer is it's tough. And you just have to do a lot of triage. So you start to say, okay, what are the quickest wins that I can knock out that are going to have a great effect? There's something called the Mikado method of software development that admits that you will never, ever have greenfield development in your life. And so you have to say, okay, what can I fix? What did I break by fixing this? And do I want to fix all of those other things to fix this one thing? So it's really just about like, okay, what can I break and not break everything? And what can I quickly undo now that it's broken? There's not a good solution to it. It's very much an intuitive, like, this feels like the right kind of thing to do. But let's talk after this because I'm hiring.
Thank you very much, Mr. Charlie Triplett. Remember, it was your first applause that counted. So that's a good seg into some upcoming science events here in Seattle. I'll quickly go through some of them, but this is by no means all the science that's happening in Seattle. The next Seattle Science Slam is March 11th, and I'll be competing. I'll talk a little bit about that later. Seattle Science Center do events pretty much every week. They have their Science in this City series on most Tuesdays. And of course, their pub events. Who's been to an event at Pacific Science Center? They're fantastic. Astronomy on Tap. Obviously, they talk about astronomy and kind of related a little bit to what Devon's doing. I'll skip down to Seattle Skeptics. They've got a planetary geology talk coming up. Geeky Comedy in Seattle do a monthly open mic in Roosevelt. And this long weekend, the AAAS meeting. Who's going to this very large science conference being held in Seattle? Now, I did my master's thesis on haptics, and they actually have an upcoming talk on Braille and other packaging tactile cues, which is very much related to what Charlie just. So there are tickets still available for the AAAS meeting, and there are so many events that are adjacent to that, like Skeptic's Guide to the Universe, the Science Podcast. They're doing an event soon. There's so much happening in Seattle. Give it a quick Google. And on that note, I would like to welcome to the stage Devon Royston.
For life, like what makes Earth such a great place? You've got the chemistry, you've got an energy source, the sun, you've got a liquid solution, lots of water, thank you oceans, and you've got shelter, an atmosphere that burns up asteroids so you don't go extinct like dinosaurs. Specifically when it comes to chemistry, we've got some really good light flexible elements like nitrogen, oxygen, phosphorus. But when we talk about life, there's a lot of carbon-based life form this, carbon-based life form that. It's actually got a name called carbon chauvinism. We kind of prop it up in a way that is entirely deserved. Like, it really earned that name because of chirality. So chirality is when you have two non-superimposable items, like my hands. They are mirror images of each other, but I can't twist and make them the same. Or like if I tried to shake your hand, you'd have to shake it with your right hand. You wouldn't know what to do if I handed you my left hand. That is chirality. And to be chiral, you need to have at least 4 different things bonded to a carbon atom. Carbon is good just because it has a neutral charge. It's not positive or negative or whatever it shouldn't be. Silicon is also able to have a net neutral charge when it's bonded to 4 things, but it's a little bulky, a little big, and really combusts easily in the presence of oxygen. When you have a chiral center, so this molecule, these look exactly the same. Sorry. These look exactly the same, but this little, whoops. Dot right here, that's a carbon atom, and that's a carbon atom. Those are chiral centers, and those, when you flip them, you get different things. You get one is a painkiller, and one is an anti-cough agent. Biomolecules are basically a really complicated lock and key. The more complex the lock and key, the harder it is to accidentally open your front door with the wrong key. That's how a lot of neurotoxins work. Like, they're fitting into the wrong key, blocking it, and making that biopathway not work. You've all seen, when it comes to energy, we've got the sun and there's food webs and whatever, but we've also got thermal vent systems on the ocean floor, which are pretty cool, and they circulate chemicals like sulfur, manganese, iron, and they generate a lot of heat from the Earth's center. You've got entire ecosystems built on the ocean floor where these little bacteria and single-celled organisms in the center of tube worms use heat from those thermal vents to make energy, to fuel their life and all of the life on the floor where there's no light. So you've also got a liquid solution. You need somewhere for all of your proteins, your salts, your biomolecules to have a party and make some biochemistry happen. You kind of want it to be polar. So if you don't know what a polar molecule is, carbon dioxide up here at the top is nonpolar. This negative kind of charge with the oxygen over here, they cancel each other out. But when you look at water, it's got positive charges down here, negative up here. So it's got a net dipole moment up this way. That just makes it really good for charged ions like salts to dissolve in water. You can also get a lot of proteins and amino acids dissolved in that. Carbon dioxide, methane, they can be liquids, but they're not really reactive, and water is a good catalyst for a lot of bioreactions. So you've also got polar molecules like hydrofluoric acid and sulfuric acid, but they'll probably destroy your DNA before you dissolve in it. You also need relative abundance. When it comes to abundance, that's about how much water is on Earth, and then that's how much water is on Saturn's moon Titan. Like, a lot. You need quite a bit. If I had to go to the North Pole to get a glass of water, then, life wouldn't be great. You also need shelter. We have a magnetosphere on Earth that bends a lot of that radiation away from the Earth. In contrast, though, it also captures radiation, and these are called our Van Allen belts. They're super dangerous. Don't go in a Van Allen belt. You will probably get cancer. This comes from having a liquid core that is a conductor. So being a liquid-like conductor that's moving around in the Earth's center, we get our lovely magnetic field, and this gives us that protection. So I'd like to talk a little bit about where else we look for life in our solar system, and those would be our Galilean moons. These two men were the first to observe the Galilean moons. That said, we do note Galileo as one of the notable contributors. But a jury in the early 20th century actually decided that Marius found them first, but only recorded them a day after Galileo did. They used different calendars. It didn't really work out. Anyways, we use the naming mechanisms that Marius decided on, which are lovers of Zeus for the Jupiter's moons in Greek mythology. But for the purposes of this talk, when I'm talking about Galileo, I'm going to actually be talking about the orbiter that went around the planet and took a lot of pictures of the moons. Specifically, it's got a magnometer and a lot of just electromagnetics, so taking pictures of things. These are our lovely moons. We've got Io, Europa, Callisto, and Ganymede. Starting with Io. Io is the most volcanically active system in the solar system. It has 300-foot-high magma tides, which super sexy. In Greek mythology, Io was a priestess of Hera who Zeus slept with because he really had a lot of fun in Greek mythology. And Hera turned her into a cow because she really liked turning lovers of Zeus into animals. It has, just like our thermal vent systems, a lot of sulfur, but there's not a lot of oxygen. So that sulfur is not oxidized into like sulfates or sulfites. It's typically dihydrogen sulfide, which is pretty analogous to water. And it is heated by tidal friction. So tidal friction is when you have a very large, think about the moon. The moon pushes and pulls on our oceans and keeps it a nice balmy temperature all year round by rubbing all of those little water molecules together as the tides go up and down. Well, imagine that instead of the moon, you have the largest planet in the solar system doing that, and you end up with a very volcanic body. That said, it is highly subject to radiation, just being so close to Jupiter and in its little radiation belts. After that, you've got Ganymede. It is the largest moon non-planet in our solar system. It is mostly made of water, and it is fully differentiated, meaning that it has like a core, a mantle, and a crust. these are our radiation belts. Here, you can see in this little red zone, that's like getting 40 chest x-rays per second. Here is Io. There is Ganymede. It's a little bit outside of the radiation belt, so it doesn't have that. Here is Europa. And out here in the far corner is Callisto. It's pretty secluded. So Ganymede is a really good example of shelter because it has this icy liquid crust that kind of prevents radiation, but it also has aurora, just like the North Pole. And that comes from having a magnetosphere. We think that the magnetosphere is due to it having a liquid iron core, which creates that dynamo effect that I previously mentioned. And I mean, it would be a good place to chill because you wouldn't have to worry as much about the radiation. Callisto, chemistry-wise, has a lot of the same things that we find on Earth when it comes to organic molecules, water, and ice, but it's geologically dead. It hasn't changed in like 4 billion years. So all of these are just crater impacts. And that's because it is not differentiated. There's not enough internal heat from tidal friction to make it an active body in the solar system, and it's just not dense. That said, there isn't a lot of radiation there, and there's not a lot going on, so it would be a great place for a space base. After that, you've got Europa, and Europa is mostly made of water. It has vapor plumes coming off of the South Pole that go 20 times the height of Mount Everest. And we think that based on Galileo's readings, it has a subsurface ocean. So you can tell right here, Jupiter's a little tilted when it comes to Europa's orbit around it. So down here, it's kind of in the southern hemisphere of its radiation, or its magnetic field, and up here, it's in the upper northern hemisphere of its magnetic field. And when it comes to Faraday's law, a magnetic field can produce an electric charge if you're moving within that magnetic field. And then a conductor that is moving in a magnetic field will create a magnetic field of its own. So when Galileo was looking at Europa, you could see that on its fourth flyby, it had a net magnetic interaction. They filtered out Jupiter's magnetic field when it came to that in the northern hemisphere. And this dotted line that goes down here is the net magnetic field of Europa on that fourth flyby. But then on its 26th flyby, when Europa was sitting in the kind of southern hemisphere part of Jupiter's orbit, it had a completely opposite magnetic field. And that means that its magnetic field is changing. It's not due to a dynamo core. It's due to something like salty water, a conductor underneath the surface of the moon that is changing that magnetic field. And because of that, we think that it's got a lot of tidal friction, so that creates heat for these cryo geysers, and radiation that is breaking up organic chemicals and recycling them on the surface, and that's what we think creates this orange stuff. It is currently the go-to place for 2025. We are going to be sending a Europa clipper all the way to this place to look and see what's going on. It's got shelter, it's got the right chemistry, it's got a liquid solution, and it's got energy from the tidal friction. Specifically, this is going to collect ejecta from those southern pole geysers and see what it's made of. You know, if it's got organic molecules or something that could harbor life. So that's some citations, and there's just so much that we have yet to explore. We haven't even landed on any of these moons yet. We haven't scratched the surface, and soon we'll be sending probes, so I hope that we pay attention to aliens. There you go. All right, do we have any questions? Get up here. What do you got for me?
So, the orange eject from the cryo geysers, have there been any investigations just based off of the light reflecting off of them as to what those might be composed of?
So we think it's organic compounds because of the spectral data. When you shoot like infrared at bonds, you can tell that they have the right hybridization. So carbon, when it is in an organic form, is hybridized in an sp3 or sp2 kind of way, which is hard to explain, but that just means that it reflects a certain energy from that infrared light. And we know that that light is being reflected based on the readings that we're getting from the different Jupiter missions. So, yes.
What temperatures are we talking about, like about those moons, like especially Europe, like Europa?
Well, Europa is, I believe, like on the surface, minus 220 Celsius-ish, which means that the ice is about the same. It's about granite, so you would be hitting rock. It is absurdly cold and only heated at the core from tidal friction. Any other questions? Cool.
Thank you, Devin Royston. I'd like to thank Devin for adhering to a rule I didn't bring up earlier. We do not use the F word here at Seattle Science Slam. We use the F word instead, Celsius, not Fahrenheit. Thank you very much. It is science after all. I get a lot of people going, hey David, how do I participate in Seattle Science Slam? Well, all you need to do is to message us on Facebook or via email. It's Seattle Science Slam on Facebook or Seattle Science Slam at Gmail. Or come up afterwards, have a chat with me. I hope Devin, Charlie, and Jared have a fun time tonight. Next up, Jared Canwright.
Thanks, David. If you can hear me, please raise a hand. Okay, saw a bit of a wave going back, so I'll try and speak loudly through this. If you decidedly cannot hear me at any point, please wave at me. Like, I would like to know that you can't hear me. Just go ahead, call me out during the talk rather than find out later that you just couldn't hear a word I said. So, I'm Jared. I'm advised in the Physics Education Research Group at the University of Washington by Suzanne Bramia. And I study the applications of virtual reality technologies to physics education. So to briefly introduce my field, I'm in physics education research. So how many people here have taken a physics class, high school, undergrad? How many survivors do we have in the crowd? Okay, so physics education research seeks to make that process easier. Or rather, it seeks to understand how students learn through research, identifying particular difficulties students have, and how we can address them most effectively through instruction. With those research findings, we feed into curriculum development, which is then applied in the classroom and again reassessed to feed back into the cycle. And now my particular interest in that is in assessing how and when should we use VR in physics education. So how many people here have used a VR headset before? Wow, quite a lot. I ask that every talk, and the percentage just keeps going up over time, which is really exciting for me and my future career prospects. So what we have here is an Oculus Quest. It's entirely self-contained headset. This is the hardware I use in my research. So it doesn't need an external computer. It's like $400 a pop. The headset and both controllers are tracked in 6 dimensions. So rotation and translation, you don't need any additional hardware, which makes this really ideal for classroom use among existing VR hardware. And so when looking at designing VR-enabled curriculum, these are kind of the things I consider. And so VR is like super exciting and engaging. Like the nice thing about this research is no matter how crappy an application I put to the students, they still love it. Engagement numbers are always awesome. But that doesn't necessarily correlate with educational outcomes. So some other more specific benefits we can get from VR for use in the classroom is you can make abstract concepts tangible, like gravitational fields, electric fields, fluxes, like more concepts deep more in mathematics that don't have a real world visualization. We can actually make tangible in VR, which is exciting. Like 3D phenomena you can observe directly rather than trying to figure out how what your professor's awkward 2D sketch on the blackboard is supposed to mean. And further, virtual worlds can follow any set of physical laws that don't really have to correlate with those present in the physical world. Like we can pause time, we can turn off gravity, we can let charges just sit in midair without doing that obnoxious thing where they try and conduct to ground. It's great. But applying VR in the classroom is decidedly not a panacea. It's not a silver bullet solution to all problems because it has a number of drawbacks. First off, it's expensive. $400 a pop for headsets is a lot. It's difficult to run in classrooms. Like, if you give a classroom full of students a lab using computers, that's pretty easy to do because students already know how to use a keyboard and mouse, they know how to use a monitor. All you really have to do is teach them how to use a software for that lesson, which even then can be designed well enough that you don't really need instruction beyond just how to interact with the content. With VR, you generally have to onboard them to the hardware, onboard them then to the operating system for that hardware, and then further to the specific application you want to use for that lesson, many of which are very much in embryonic stages of development, and their UX is decidedly not well fleshed out. So, and further, assuming you can just give every single student in a classroom a VR headset is a very poor assumption for a multitude of reasons. So not all students will be able to use a VR headset for whatever reason. Not all students will be interested in using a VR headset. While it's exciting to most of us, that is not universally the case. For example, what I'm going to be talking about is a lab we ran actually this quarter, just a few weeks ago, only 2 weeks into class. And so a VR headset blocks out your entire field of vision. And imagine doing that in a room full of strangers you've met once the week prior. That is not necessarily a comfortable experience. And for that reason, or whatever others, we need to respect any reason for not being interested in using a VR headset and make sure that those students don't suffer any detriment from our efforts to introduce VR in a classroom. We have to design such that they are included and get the same educational outcomes as everyone else. So, what I'm going to be talking about today is something we came up with that we think solves a unique problem we can't do any other way and justifies those drawbacks I was talking about. And so the little chart here is kind of a representation of the scientific process. So you have some unknown system behaves in some unknown way. You first do like qualitative experiments. You try and figure out generally how it works. Like gravity pulls things down. Great. Now, then you form a model that you can test. So gravity pulls things down always, or there's some places where that breaks down. Maybe I suppose there's a gravitational field that follows 1 over distance squared dependence between 2 points. I can test that. I can collect data. I can check whether or not that model is correct. And I follow this process until I come up with something, until I come up with some model that is able to handle all of the tests I can throw at it. So that only really works if I don't already have an idea of how the system works. And trouble is, in first year physics, all the answers are on Wikipedia. Or you might have even just learned them through lecture. There is not really an opportunity to do authentic experimentation from scratch. You can find any of the content that we might reasonably give to a first-year physics student without being super, super mean. They can find the answer very quickly. And so labs become not a process of experimentation where picking a believable model and finding it to be wrong is okay, but a laboratory experience where you're working with maybe janky equipment in a limited time frame, trying to figure out how do we get this to match the outcome we know to be accepted and true so we don't fail our lab report, rather than actually trying to go through an authentic sense-making process, figuring out what chain of reasoning can lead us to the correct conclusion here. Instead, they're just working backwards from the correct answer. I see even cases just fudging data to make it make sense with what they believe to be true. And so this is the problem we're trying to solve. And so, again, VR labs can follow any set of rules that we want them to. Reality can be whatever we want it to. And so we invented a new type of matter that works analogously to electric charge. We have positive charge, and we have negative charge, and there's a law named after some dude that dictates how they attract or repel each other. So we made up something analogous to that, and we called it MINT. If anyone's familiar with Terry Pratchett, instead of quarks in that universe, they have thowns, which instead of up, down, charm, strange, top and bottom, are up, down, sideways, sex appeal, and peppermint, which inspired minty particles. And they interact a bit like this. This is what happens. You take just a bunch of minty particles and you throw them next to each other and let them react as they will. The bright green one's a little bit mintier than the rest. This is why it jerks around a little bit more once the GIF starts running. And so we constructed a virtual lab where students have access to positive and negative charges and minty particles, and also virtual measuring tapes and force meters, like those little spring scales. And their job was to figure out what rule governs what minty particles do. And so they already have some familiar interactions that are implemented there. So like these are supposed to be positive yellow and negative purple charges that interact much like they do in real life. The students had to verify that, yes, indeed, I, the developer, did actually put in Coulomb's law, which is how these work in the real world, and not some other function to screw with them. And I didn't screw with them. This was accurate. But so we gave them these interactions that they're familiar with. So like particles repel, positive repels positive, negative repels negative, and opposite charges attract. Then we gave them minty particles. So this minteraction, if you will, is entirely unknown to the students. So before we ran the lab, you could have counted the number of people who know this function on one hand. You can't find it on Wikipedia. You can't find it in the textbook. There is no way to possibly know the answer ahead of time. But so you can see it acts kind of like maybe a spring, like kind of harmonic motion. Maybe there's a 0 point where it turns around. Give y'all just a second to try and guess the function if you're feeling super savvy. So this is the function. It's a bit complicated, but just to break it down really quick, R naught is a 0 point. R naught is 0.5 meters. And so right there, at a distance of 0.5 meters apart, the force exerted on each particle is 0. And so when the distance is smaller than 0.5, they repel. And when it gets greater than 0.5, they start attracting and pull each other back toward each other. And so the force function follows roughly this graph. Now here's what the students found. So this is just 1 over r squared electric force, just like with positive and negative charges for reference. Most students actually thought that the force function was a spring, and the force of a spring is just a linear equation. But you'll notice around r naught here, around 0.5, the linear approximation is not that bad. It's actually fairly close. And so we didn't give them quantitative tools, like be able to actually look at the numbers while they're coming up with their model to test. And so based on only qualitative observations, that's a pretty good guess. Whoops. And so their job was not to find the right answer, but rather to determine a model based on qualitative exploration, figure out exactly how they're going to test it, and their criteria for saying this model is supported or no, we've disproven this model, and execute on that. And they did, which is super exciting and not something I've ever seen in an introductory physics lab. So students were able to generate testable hypotheses based on familiar patterns. So they all recognized, oh, we've seen things go back and forth in a relatively even pattern before. Last quarter in mechanics, we saw that happen with springs, so let's try a spring, which was a really close guess. students were able to make evidence-backed arguments to accept or reject this hypothesis, and universally, they made the correct judgment. Whether or not they accurately guessed the model, they were all able to say, yes, this is supported, or no, this is rejected, which was incredible. No one tried to hold on to the idea of, oh no, we must have had bad data, or oh no, the equipment must have been janky. They were all able to confidently say, no, our initial guess was wrong, and that's okay. That's a process of science. And now these results are going back into development of curriculum accompanying this lab for next quarter, where we'll take interesting ideas from students' lab reports and form research questions around them to determine exactly how VR is uniquely providing affordances that no other medium can. Now, if that's the kind of experience you'd like to have in your classroom, please make some noise. Are there any questions? Come on up. That's a fantastic question. Thank you for asking. The question is, do I see VR as being a supplement to existing means of instruction, or as something that will eventually take over instruction? And I definitely say the former. VR should definitely be used as a supplement to instruction in physics and every other field. I feel like there are some cases, hopefully this one, where VR can uniquely be used to enhance education in ways that no other medium can. In that case, yes, I say that's entirely appropriate and should be used that way. However, it's not a silver bullet. There are a great many ways to use VR in a way that is not distinctly helpful and is just, what if we did this thing we can do in real life, but in VR? And actually is a big waste of developers' time and contributes nothing. Like, imagine exploring gravity in VR. Just flat surface of the Earth approximation gravity. So that's a great point. I don't really see VR taking over as a sole means of instruction really in any classroom environment. And I really hope that developers of educational applications focus on where is this uniquely helpful. Any other questions? Sorry? The question was, what hair product do I use? American Cure hair fiber. That was not a question I was expecting to answer. Thanks. Any others? Thank you.
Okay, now time to announce the winner. Now, I do things slightly differently to Olga. Can all three of the participants, please come up to the front? The loser will be shot out of a cannon into one of Jupiter's moons. Charlie, Jared. Okay. In third place, with a very respectable 94.6 decibels, is Devon. Put your hands together again. In second place, with a very close 99.4 decibels, Jared, making Charlie our winner at 102.3 decibels. One more round of applause for all three of our contestants. Now, and here is a $40 gift voucher. Now, thank you very much. You may all take your seats. It's very unusual that we have 4 men up here tonight. That's the first time this has ever happened with Seattle Science Slam. Not a good thing. Normally, there's better gender representation. So if you'd like to participate, come up and have a chat to me later. Thank you very much. We'll hopefully see you again on March 11th, where I'll be competing, and we'll see where I fit on the decibel score. Thank you very much.